Oh,
Um,
nice. Okay,
Continue.
great.
So yeah, so if you look right here, you can go to youtube.com watch,
Oh,
or you or you
nice.
can or you can or you can watch
Okay,
the recording. Yeah.
okay, that's
So
great.
what? So yeah. So I think that the easiest way for you or for um, RAs or lab
Hmm.
managers to analyze the
Yeah,
pupil data would probably be to access it via the CodeOcean container. So that's what I'm going to show
okay,
you how to do,
okay,
or how to actually process the data through the CodeOcean container.
okay.
CodeOcean is kind of like, are you familiar with Docker?
No,
Where it's like a container that encapsulates your kind of entire analytic pipeline.
okay.
So it captures all of your dependencies. So you're not going to run into the issue where you try to, install GazeR on your computer, your personal computer, and then you're
Hmm.
going to have all of these like incompatibilities, or you're going to have trouble downloading certain packages. So GazeR requires certain packages, and some of those packages don't really play nicely on certain versions of R and RStudio, and depending on if you have a Mac versus PC. So the container kind of eliminates all that. So essentially everything is within that container, and you can just open up a virtual RStudio session and you can run your analyses through that, and then save all the data, and then you can, export it to MATLAB if you'd like. But if you want to follow the GazeR paper, you can try downloading it in R. You have a Mac, so it's usually not an issue to run some of those packages. But if you have a PC, sometimes you can't get those packages to load. So the container kind of eliminates all of that headache.
Sounds great.
So yeah, so you would just go to the GitHub page, and then what you would do is just click on this little CodeOcean button here, and that takes you to the CodeOcean capsule. So what you do need to do is you need to sign up for CodeOcean for you to actually duplicate the capsule. I already have an account, so I'm just gonna kind of sign in to that. Or not. Oh, that's why. Let me go to the container, and you can see my screen. Can you hear me?
Yeah, I just muted myself because there's background
Oh,
noise, but yeah,
oh,
I hear you and
okay.
I see your screen very well. Great, thanks.
Okay, awesome. So yeah, so what you need to do is once you click on that, and obviously once you have an account, what you need to do is kind of duplicate this capsule. I've already kind of set this up for myself, but you would just have to duplicate the capsule by going to capsule and duplicate, and then it would open up like a copy right here, and then you'd be able to edit it. But what you can do from here is you can actually upload the files. I've already uploaded these EDF files right here. So like QEEG009 and QEEG0010, which correlate to the QEEG study. So you would just need to upload these EDF files, and you can create a new folder if you like, or you can just upload it to wherever it goes to. So you just choose the files, and then you would just click on the EEG files that you want to download. And these are the EDF files that you get from Psych Toolbox. So after the experiment is complete, these EDF files will reside in the folder, the MATLAB folder that you designate.
Okay.
And you would do that. So I'm not going to upload those. And these files are very big, so I'm only doing a couple of them because they take anywhere from a couple minutes to 10 minutes to process. So yeah, so once you've imported the EDF files, then what you can do is you can actually launch a virtual RStudio session. So if you look right here, there's a little RStudio button, and you can just launch that. And then it'll prepare the environment. Again, it installs all the dependencies that is required of GazeR, so you don't have to do that. and you're not going to have to run into errors and figure out how to get the packages installed. So wait for that. So there we go. We have a virtual RStudio session opened up. I've created this markdown file called in-young test, and I can give that to you, and you can kind of just use it whenever you try to, if you're interested in analyzing people data. What you need to do is you need to install the important packages like tidyverse, and you also need to install GazeR, and that's what this load all does. It installs all of our packages, but you could just click that button and it runs all of it for you. There we go. All right, so everything is installed that we need with this kind of chunk right here. So what we need to do next is we need to load or tell the computer where the files reside. So here is a package that I really like, because you don't need to set the working directory directly. It automatically knows where the directory is, or the package directory is. So you don't need to set any, so you don't need to set anything hard, and you don't need to set any hard. It just, so whatever computer you're on, it actually populates the actual working directory for you. Because again, I'm JasonGeller, my directory is like JasonGeller users, yours might be a different directory, but here it kind of eliminates that, because it just uses with the folder and your computer setup for you.
Got it.
So we have to set the directory where the actual files are. So I'll just do these sequentially. So I've done that, and then we have to set a directory for where we want the EDF, or where the EDF files live. So that's where the EDF files live. So it's in the capsule code. So capsule code, and that's where we have the EDF files. I'm going to delete these for right now, so they're not there. Okay, and then we need to save a directory for our CSV file. So these are saved as CSV files. You can save them, whatever's convenient for you, save them as that. I just like working with CSV files, and I think you can easily read those into MATLAB. So again, these are just kind of getting all the names of all the files. So file list is just essentially just the list of the names of our EDF files. So QEG0010 and QEG009. So we have that, and we can just run this all as one chunk. All right. So parse EDF is a GazeR function that I created that takes that list that I saved. So QEG10, QEG9, it could be QEG8, 7, 6, 5, 4, 3, 2, 1. And what it does is it actually batch processes all those files. So basically it extracts the important information from those EDF files, and it puts them in a nice data frame so GazeR can analyze it. So you get like a blink column, a pupil column, a trial column, and a subject column. And that's what that does.
Okay.
Again, it is very important that your directory is where the files live, because then you will get errors. So this output directory, you can save this so you can create a folder and you can save the CSV files in a separate folder, and that's what you should do. But for this, I'm just running everything within the same folder. But you'd probably create a directory called CSV files and then have the file saved there. So this output directory, the CSV directory, would be some other directory. It would be CSV files, QEG experiment. But you can play around with that if you'd like. But yeah, this just saves all the CSV files in the same place where the data lives. So we can do that. So yeah, so basically what this does, again, as I said, this just reads each EDF file and then extracts the important information. Depending on what the sampling rate is, it can take a very long time to process. Megan's experiment, I think, was 500 Hertz, and there's 240 trials, so it could take maybe a couple minutes to do it for each file. I've run probably maybe 30 or 40, and it's probably taken maybe 40 minutes, so not too bad.
Okay.
So who runs that? So do you have any questions while this is processing?
No,
And
this
you
this look
you can actually take this, and then you can pretty much just run through it. So you can run each code chunk to analyze the data, and it should work. You just have to change a couple
right,
things.
right. Okay.
So yeah, after this is done processing, it'll save the CSV file into the directory that you specified.
Okay. So can you go up a little bit
Yeah.
for those lines where you imported those libraries?
Yeah.
Yeah. So where is GazeR there?
So since this is a capsule, GazeR is just
Okay.
defined by all of the R files that are here. So there's an R directory here, and these are all kind of the encompassing or the important functions for GazeR that are using.
Got
So
it.
this load all will
Okay.
just take all these R files and just load them.
Got it. Okay.
If you wanted to download GazeR from GitHub, you could do that as well. So you can, unfortunately, I haven't put it on CRAN, which is where all of the packages live, if they're legit. But I haven't done that yet because it's kind of still in alpha or beta. So I'm making changes constantly. So I don't want to make any final decisions on it. So you can't just, install GazeR from like the repository, like what you would normally do for R packages.
That's great.
Yeah, no, but I will send you this. And you can pretty much just always use this kind of basic script to analyze the data and get what you want from it.
Okay.
Yeah, so you wouldn't. So yeah, okay. So the parse_cdf function did what it's supposed to do. So yay. If we go back to our working directory here, we see that we have two new files. So we have QEG10 raw pupil and then QEG9 raw pupil. So then those are the CSV files that we've extracted all the important information from. So we can use GazeR to process it. So after we do that, what we need to do is actually call list files again. So we need to create a new list with the CSV files. So what you would do is you would just you would take the path. So we have the CSV directory, which is the same directory where our files are, and then just pattern, which is .csv, and that should pull all of our CSV files. So if we look at that, let's see. Yeah, so we have a list with our two CSV files in there, so that's good. That's what we should expect. And there's another GazeR function that I created called just merge GazeR files. So that takes the CSV files, and instead of reading them individually, it just kind of, you take that list and it just kind of combines them or merges them into a single data frame. So you'll have, participant 1, participant 2, all within the same data frame or same object. So we can do that. So yeah. So now we have a object called PD, and then that has essentially the information that we need. So it has our subject, it has our time variable, has our trial variable, our pupil variable, X, Y coordinates, blinks. So zeros are they didn't blink, ones is that they blinked, and then message is just our message variable. And if you wanted to, again, you could just take these CSV files and you could just read them into MATLAB as well if you wanted to do that, if that's where you felt more comfortable working. So this is where it gets fun. So in our psych toolbox experiments, there's certain messages that we send, right? So we have some type of message like, exclamation point V trial var, and then we'll save it as like accuracy. So it sends a message every time there's like a new trial, or you want to send what condition that trial was. You're familiar with that, right? Within the MATLAB Psych Toolbox framework.
Yeah.
So unfortunately, the EDF files, they don't, very conveniently save all that information in nice little columns. So I created a function that will actually take all those important message variables, so our condition variables that we need to analyze the data with, and it puts them in a CSV file. It's not pretty, so they don't save them, explicitly as, numeric or integers or factors. Like, you would have to probably do that after you process that, because there's really no way to create something like this that automatically can guess kind of like the variables that you're going to want to extract from the EDF file. That's just how it is. And EDF files are a pain to try to process. It's a disaster. And SR obviously is a commercial company, so they need to make money, and a lot of their algorithms are, kept up in lock and key. So you don't really have access to any important stuff. So a lot of this stuff is, approximates for what they do behind the scenes. So it's not the prettiest sometimes, and it's not exact, but it's pretty close.
Okay.
So once we do that, what we need to do is we need to extract the messages from the EDF file. So again, for GazeR, I created a function called find messages EDF. So this takes the file list that we've. Did I miss something? No. Yeah. So this takes file lists. So these are going to be where the names of our EDF files, because we need to reprocess the EDF files and extract the messages. So file list is where our messages are stored, our EDF files are stored. And then what we need to know is kind of our variable names. So trial ID is pretty common across EDF files, so that's just what trial it is. In our experiment, we had conditions called queuing and accuracy that we want. So whether it was queued or non-queued, and then whether they got it right or wrong. And these are all variables that we saved in MATLAB. And then we also need a pattern. So we have a patterns argument here. And these are the exact codes that you would find in the MATLAB Psych Toolbox script. So essentially what you would need to find are kind of where we called these exclamation point V trial variables. So we would need to include those kind of exactly how we have them in the Psych Toolbox MATLAB script. So we would just copy that, and then we would extract those and save those to our working directory. Again, you probably want to have a separate folder called messages where all those messages would go there. But for the purposes of this tutorial, I just throwing everything in the working directory.
Okay.
Let's see here. Did I mess up something? Yes. All right, so that took our EDF files and then saved them as messages. So I just saved them as EDF behave data, and we can take a look at what that looks like. So again, we have trial, queuing condition, accuracy, and then subject. Do they have better looking? Yeah. So it looks something like this. So basically a data frame with all this information in there. So whether they got it right or wrong, with the condition and then the subject. Again, these are all important variables that we need. We can't really do anything without those variables. For this part, I'm going to delete these pupil. Okay. So then we need to call this, we need to actually get the file names again. So we have to look for CSV files for our messages because we're going to merge them. So there we go. We have our two file list message files. And then we just merge them like we did with the other files. So let's look at messages. Yeah, so there we go. So we have an object with our trial information and all of our subject information. And then what we want to do is just merge those messages with the full pupil data frame that we have. So yeah, so there we go. So now we have all the data that we need to actually analyze the pupil data. So again, subject, time, trial, pupil, the message, and then also the condition that they were in, and also if they got it right or wrong. So now we're actually, we're able to actually start analyzing this data. So this particular function right here is called, basically extends the pupils. So it's been recommended that if you have, blinks in your data, that you should extend them. So extend them a little bit before the actual blink took place, and then extend them a little bit after the blink took place, because those values are most likely spurious. So that's what the extend pupil function does right here. And this just extends it 100 milliseconds forward in time and 100 milliseconds backward in time. And this is actually modifiable. So if you want to set it to 10 milliseconds or 20 milliseconds, some people set the fill backwards to, shorter than the fill forward. You can input whatever you want in here. I usually just do 100 milliseconds before and after, but you might want to play around with this and see what gives you the cleanest data. This Hertz, this Hertz argument here is just what the sampling rate is. So if you sampled at 500 Hertz, you put 500 there, or if you sampled at 250, that's pretty self-explanatory. And then you run that. All right, so that ran. So if we look at pup extend, what we have now is we have another column here called extend pupil, and then that is just a column that has our pupil data, but with the variables 100 milliseconds before a blink with NAs and 100 milliseconds after it with NAs, if blinks occurred during that particular sample. So once we do that, what we do usually is we smooth and interpolate the data. So what I've seen, if we're going to do, again, I recommend linear interpolation, and I recommend doing interpolation first and then smoothing, but you can actually switch that if you'd like. So you can smooth the data first and then interpolate it. If you're doing just linear interpolation, there's really no difference what step you use. So if you said the step first would be, smoothing, there's really no difference. But if you do cubic interpolation, there's actually a pretty big difference to where if you do interpolation first, there's kind of more of an exaggeration or a larger effect. I think I can, here, I will do that. And then for the filter, there's two different types of filtering algorithms we have. So we have a moving average, which is just a 5-point moving average filter, but you can also do a Hamming window as well if you want to do that. I just usually use a moving filter.
Okay.
So type, again, linear or cubic. There's really no other options. Hertz, again, what's the sampling rate? And then N is just what you want the moving average to be. So sample 5 times, you want a moving average of 10 points. This is just kind of the default value for this.
Got it.
So you run that, and then it just says performing linear interpolation, and then smoothing the pupil trace with a moving average. So then after that, what we can do is baseline correction. And there's two different types of methods you could use. You could use a divisive method or a subtractive method. It's common for a lot of us to use a divisive method. Some people think that you should only be using subtractive methods. Within GazeR, I've kind of built in kind of the best practices. So if you're going to use a divisive type of method, what I've done is instead of taking the baseline for each trial, it just takes the baseline from the grand average and then uses that to calculate the proportion change. And that eliminates the influence of very small pupil values on the baseline that could have exaggerated effects. So it could make your proportion change very large.
Okay.
So this is the variable from above. So the smooth interp 4. So pupil column, you need to label what the column is. So it's just pup interp. The baseline duration that you want. So if you want 500 milliseconds before an event, or you want 1,000 milliseconds, whatever you want. But it has to be, the duration is everything before this event that you're of interest. So here it would be sound, let's say. So this would be 500 milliseconds before the sound played. So you would do that. Hopefully this works. Yeah. So here we have kind of just the baseline corrected people values. So yeah, there's that. I think sound is one of them. Hold on. Or is it noise? Yeah, so you can kind of change this to wherever the event is. I think, can't remember what the messages were for. Yeah, so there's no event called sound, which is why all the baseline corrected values are NA. So we just have to pick something. So let's say we want to do 500 milliseconds before start CDW. So we just look at that and then just rerun that. Yeah, so now we have a baseline corrected value. So this is proportion change from baseline, and we have that here. And that changes. Next, and these order of operations can obviously be changed if you think that there's a better order. But what I do next is I just delete, or I look at, I count missing data, and then remove participants that have lots of missing data. And then you can set a missing threshold here of whatever you'd like. So we recommend like 20% missing data, but you can also change that to 50% missing data. So you keep individuals in there as long as they don't have more than 50% missing data. And that's what this does. So if you run that, what we get from here is number of trials excluded, which is 25%, but participants taken out is just missing. So that means that no participants were taken out of the function. And this automatically removes the participants. So if you didn't want that to happen, you might want to do something like at this level here, and then just do your own type of like missing count if you don't want the actual trials or actual pupil participants taken out. So do you have any questions so far?
No, these look just very straightforward. Great, thanks.
Yeah. So here, and again, you can probably skip this, but this would create a histogram of the pupil values, of the raw pupil values, and then you would try to come up with a cutoff for unlikely values at the high end and the low end. You don't really need to do this, especially with the new functions that I've created with the divisive baseline correction, because now the baseline correction is the grand average. So that should eliminate any kind of extreme results. But if you wanted to, you can actually look at the histogram of the pupil, and then you can filter or get rid of pupil values that might be unlikely. So it's generally recommended that you don't perform this on standard deviations. So sometimes you'll delete pupil values 3 standard deviations above or below. That's generally been recommended against. It's been recommended that you look at a histogram of the data, and then based on that, decide unlikely pupil values. So you can do that. So that's what this particular function does right here. So this just eliminates, pupil values, or this keeps in pupil values greater than 2,000 and then less than 7,000. So anything, less than 2,000 or greater than 7,000 are just taken out of the actual data. So then next, what I do is I perform kind of like a second pass of the data using the median absolute deviation score. And this just there might be some instances from sample to sample where the pupil change is just not realistic. So it might go from 0.03 to 0.55, something like that from sample to sample, which is just not realistic. So this actually does like a second pass over the data to eliminate some of those spurious values if they're still left over. Looking at the median absolute deviation. So if the speed from sample to sample is greater than the median absolute deviation, it just throws those data out. This is just a second pass. You shouldn't expect to throw out too much data, but this is just another way to kind of, clean up your data to make it as clean as possible. So after we do that, what we do is we essentially make our data so that it starts at onset. So some type of condition onset. So in our data, we might want to start the data at noise onset or start, check the word. And that's what this particular line of data would do right here. So this basically sets our 0 time point to the stimulus onset. So our 0 point would be start the word. So that's what this does right here. And what we usually want to do is we want our time 0. We want to go back a little bit in time. So like, negative 100 milliseconds or 100 milliseconds. And then it ends at 2500 milliseconds. So this is just what this line, this kind of code does. And then obviously, so this 0 onset, you need to make sure that you put the correct event, which would be start noise. And then you can run that and it should run each time. So after you've, after you've kind of created a 0 onset type of data frame, what you need to do is you need to downsample the pupil data. So that's what this downsample gaze function does. So it takes your pupil onset variable from above and essentially just downsamples it or decimates it. So you can create whatever bin length you'd like. So you can do it every 200 milliseconds. You could do it every 50 milliseconds. You can do it every 500 milliseconds. You just have to put it in here. So you might want to do bin length 500. And then you would get a data frame that is sampled every 500 milliseconds. So you'd have 500 milliseconds, 1,000 milliseconds, 1,500 milliseconds. You need to tell it the time variable, which is time 0 from above. And that's the variable that we created right here. So time 0. And then what we need to do is we need to kind of have variables that we're aggregating on. So the variables that we care about are subject, condition, time bins. You might want to look at kind of more trial level data. So then you would just put trial in here and then you get a data frame with subject, trial, condition, and time bins. And then type is just a variable, whether you want to look at pupil data or gaze data. For us, we just want pupil data. So type would just be pupil here. You don't need to change anything there. And then after that, you're actually, for you, I mean, I don't know what you're comfortable doing, but at this stage, you can actually save this as a CSV file, and you can actually read it into MATLAB, and you can do your data analysis and your plotting from MATLAB once you get here.
Yeah.
Because right here is when you have your clean data. The data is cleaned here. Yeah.
Right. And also for any across subject statistics, we need this time course, right? So
yeah,
I think it makes a lot of sense to save the data here. Great.
Yeah, so you save the data here, and then you can, so we could do something like write CSV, and then you do time bins 1, and file equals, I don't know, time.csv, whatever. And then it would save, and then you can just pop it into MATLAB or whatever program you feel comfortable using. So yeah, and then you can obviously plot in R if you want. So this is what this is kind of just the notebook that I gave Megan, and she was able to kind of go through the data, each step, each chunk, and she didn't really have any problems doing it. So I don't foresee, RAs or anyone having problems doing this. And then this is kind of just a base ggplot visualization type of code where they can just plug in this data and create it. And then change some of the title axes and so forth. But yeah, so I mean, that's essentially what it is in a nutshell. Again, once you get to time bins, the data has been cleaned. So you're aggregating, you're cleaning it up, and the signal, you know, should be pretty clean. You don't have to do any more cleaning at this point, and you can run your analyses at this point. So if you want to get, you know, max or mean, again, you can do that in MATLAB. You could also do it in here. If you just want to do like cluster permutation or growth curve, you can do that too. But this is kind of the main file, or the most important file, because you can take that file and you can read it into different programs if you want to, whatever you're comfortable in doing. But yeah, so I mean, that's pretty much it.
Sounds great. Yeah.
There's a lot of steps, especially when you're trying to read in EDF files. But that was something the reviewers wanted us to do, is be able to just take the files from the SR eye tracker and just be able to read them in without using their proprietary software.
Okay. Wow.
Yeah, and this is all outlined. This is all outlined in our paper. So if you want to look at that too, yeah, kind of, it goes more in depth into the different functions and why we did what we did, the philosophy behind them. But yeah, so I think obviously if you have any issues getting this to run or work, you can obviously reach out to me, and I can get it working.
Okay. Yeah, this has been really helpful. Thanks so much. I'll watch this one more time, and while I read through the paper, and then while I also practice with the real data, I'm pretty sure that once I experience that for a couple of data files, then I'll be pretty much comfortable with this, and then I'll be able to try training our new research assistants with this. So yeah, thanks so much. That's great.
Yeah, and you just shut down, and then any files that you saved during the session will just save here, and then you can just download them. So like, oh, I want to download this file, and I want to download that file. That's it. But yeah, I mean, I don't know if this, you know, this capsule is easy to understand and use. Again, it requires you to have an account, and I think you get 20 hours a month of, you know, computation time. And you can have up to 20 gigabytes of data stored on here. So I don't think it should be a problem to do this on the capsule.
Okay.
But yeah, you could also just do it you can just download R on your computer and then try to download the packages. But especially if you're going to be reading in EDF files, I've gotten a lot of complaints about. So the EDF package that we use to read the EDF files is not something that I created. It's kind of a third-party type of package that someone else created, and it just doesn't play nice with newer versions of R. So there's been lots of issues with getting that to work, which is why I created this capsule, because it's always going to work, and you shouldn't have any issues getting it to run.
Got it. Okay, that's really good to know.
But yeah, no, if there's interest within the lab, if you guys are going to do more people stuff, I mean, you can also invite me for a talk at some point in this fall semester, and I could just give a tutorial on this for interested folks. I just didn't have time to do it before, you know, the end of the month here.
Right, I understand that. Okay.
Yeah.
Great.
Yeah.
Yay. So yeah, I'll stop recording here.